happy to have Ryan Lanzetta telling us about bootstrapping LSM anomalies.
Okay, thank you. So thank you for everyone for still being here at the last talk. And thank you, of course, to the organizers for allowing me to speak here. So I'm going to tell you about some... So I'm going to tell you about some work that I finished last year, and some also some ongoing follow-up work. So if you're a lattice person, then what I hope to tell you about is some useful constraints that you can understand if you're thinking about lattice models that have interesting symmetry constraints and are described by conformal field theories of low energy. And if you're a field theory person or a CFT person, then I hope to just tell you very universal statements about CFTs in general. So the organization of my talk will be just to give you some motivation. Then I'll discuss symmetries and anomalies in 1+1D CFT. Then I'll discuss a little bit about bootstrap and bounds, and then finally I'll end with a summary. Okay, so basically what we want to do is start with some lattice Hamiltonian, and we want to ask what is the what could quantum field theories could possibly describe this lattice Hamiltonian. And at low energy. So this is a pretty hard question. So we can refine the question and ask instead, what about conformal field theories that can describe this lattice Hamiltonian? So if you think roughly about phases of matter, usually they're separated into different gap points and then critical points separating them. And so studying the CFTs usually, in most cases, tells us the universal information about the low energy features of this set of Hamiltonian. Okay, so the dream of bootstrap is to be able to turn this fuzzy, weird space into some nice object that we understand very well. And so the thing to have in mind here is that we really want to take the minimal set of information that we can understand about this Hamiltonian and sort of develop some program which allows us to make very general statements. So the things that we should have in mind when we are talking about what constraints we want to include are things like symmetries and anomalies. So sort of to illustrate or to reiterate what Eugen was telling us the other day, somehow if we can identify some symmetries and anomalies on the lattice model, these will be mapped somehow to the CFT. And this will be sort of the minimal amount of starting data that we can use to start to chip away at what the kind of CFTs we can get to look like. So a particular set of constraints that we can identify on the lattice are ones which lead to so-called Liebschulte-Mattis type theorems. And very generally, these kinds of theorems will allow us to conclude, for instance, that the ground state of a lattice Hamiltonian, subject to the appropriate symmetry constraints, cannot be trivially gapped. So these days, this sort of thing is understood as an example of tooth anomaly matching. There are many different kinds of symmetries that can lead to these sort of constraints. Most of them involve some kind of mixture of spatial and internal symmetries. The one that I'm going to talk about today is one which involves a translation symmetry by one site and an internal symmetry that's realized projectively at each site. So concretely, you can think about the Hilbert space of this lattice model as being some tensor product of some finite-dimensional unset Hilbert spaces, and the symmetry generators will be globally generating a Zn squared symmetry, but at each site, the individual tensor factors will obey some sort of projective symmetry relations. So turns out that these assumptions, translation symmetry by one site and some projected symmetry representation by each site, is sufficient to get this kind of pixels minus constraint.
This one plus one.
1 plus 1. Yeah, and by the way, I should say, if you have any questions, please feel free to interrupt. Yeah.
Why it is the n square? This is our assumption.
Yeah, this is sorry. So this Zn squared is the simplest kind of group, basically, that could give you such a constraint. At least if you have this version where you have translation and internal symmetry. So yeah, that's just an assumption.
Yeah, this is a simplest assumption for what?
If you want to use the version of LSM where you have translation, a mixed anomaly between translation and a projective representation of the internal symmetry.
Okay, I see.
So it's the simplest group that emits projective representation. Okay, so now if we find that this lattice Hamiltonian is described by a CFT, what kinds of things might we be able to say about the CFT? So what we can say is that somehow the symmetries of the UV model should be mapped into the symmetries of the CFT. In this talk, I'm going to assume that, or we're going to imagine that if we have a lattice model where some CFTs arise, where in the lattice we have this Z translation symmetry, we're going to imagine that in the IR, this translation symmetry is realized as an internal Zn symmetry in CFT. So this happens, for instance, in Heisenberg chain, and also in other examples for n larger than 2. This sort of thing happens. Roughly, the intuition for this is that in the lattice, the symmetry defect of the translation symmetry is like adding one site to the system. And when you do this n times on the lattice, you essentially recover a linear representation if you started with a linear representation just by the way that the tensor product of the projector representation behaves. Yeah.
So, did I hear correctly that inserting a symmetry defect with a lattice representation, so now it's just shouldn't I be able to define that fixed size?
Well, it's a spatial symmetry, so.
Any H field along space
Agreed. Thank you.
It's easy to see if you're talking by 2 sides. The number of sides is all you're going to come back, transform by 1. It's kind of like a whole.
Like if you like, I think you can also just say like the boundary conditions I impose on the last operators is like conjugate T with conjugate this operator at site L by T is equal to operator at site 1, something like that, and that kind of removes that site, I guess, basically. So
Thank you. That's very helpful. So
yeah. 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 So yeah, this is now going to be an assumption that the translation symmetry is going to be realized as Zn. Zn is not the only thing that you could have, but it's sort of the simplest one. You could have like Z k times n or k symmetry as well. The important thing is just that something like a Zn is the minimal thing which can carry the anomaly of the lattice system. And actually, if you look at Nugent's paper on this subject, he writes the explicit form of this kind of anomaly on the lattice, which is very nice. But it turns out that in the IR, the consequences of the anomaly that we're going to assume we have is going to be at this point. Some 3 co-cycle, and I'll explain how this feeds into later bootstrap. Okay, so what do we want to do with all this information? So there are a few things that we can try to do. Some are more hopeful and some are already done. So the first thing we can do is compute a universal upper bound on the scaling dimension of the lightest operator of the CFT, which is charged under the global internal symmetry that we assume is CNQ. So what this result means is that if we assume that we have some anomaly in the UV, then, and our system is described by a gapless CFT, then the gapless degrees of freedom which are charged must exist at low energy. So we can't just have sort of the charge degrees of freedom for all of the symmetry be gap or gap somehow. So that's sort of intuitively clear, but we can really quantify it with bootstrap, something like bootstrap. So sort of something that's ongoing, which is a program that I hope to finish someday, is to explore the implications of the fact that every CFT has at least one stable conformal boundary condition. And I think this should have some important implications for a CFT, because there's a lot of constraints that are present from when you're studying a CFT with boundary. So far, the main result I have is with some other assumptions. I can, in this context of a ZN cube symmetry with this, what I'm calling LSM anomaly, we can get some upper bound on the dimension of the lightest non-local symmetry defect operator. So this is like some operator that lives in a Twisted vector of the lower space. So really, like the main question which motivated all this work, and which is still completely open, and I think it's probably very hard, is whether there's any way to prove a lower bound on the central charge of conformal field theory that has a unique vacuum and this LSM anomaly, or really any anomaly. Like you can find any anomaly out there for discrete symmetry, let's say, and you can find some way to prove a lower bound on the central charge. That'd be extremely exciting. So for this particular case, it turns out that you can find theories that have this anomaly if you take n-1 free compact bosons and couple them together, preserving the appropriate symmetries. So the question here is really, can we do better than that somehow? So add interactions or construct some very exotic other kind of CFT that we just don't know at all.
How is this, so you said it's assumed that the symmetry acts on gapless degrees of freedom, right? But the technical matter, what did they actually do to prove this upper bound?
Well, what I did is use modular bootstrap.
Okay.
So you can import
How do you incorporate this assumption, the anomaly forces?
that's the result. Or you assume that you have a CFT with the anomaly, and then you can quantify what's the charge gap of this CFT if it has this anomaly. As a function, the only input is the central charge of the CFT.
The question is how do you incorporate the fact that you have an anomaly?
Right. So I'll explain that. I'll explain how you incorporate that.
Yeah, for the last one, what's the result here? So it has
This
a
last one?
lower bound for the three bottom?
It's not a lower bound, it's just an example. There's an example of a CFT that has this anomaly for n-1 free boson, so that's equals n-1.
This has a anomaly?
It has an anomaly, yeah. Compact boson.
Okay.
Yeah. Okay. So, so these are the goals, and so now let's talk about how we can try to achieve them. So, first I need to describe symmetries of a CFT, and we'll start with just talking about the whole of the CFT. So, and by this I mean really just I have a 2D conformal field theory. There's no additional. So these days people are talking about symmetry TFT and things like that, but the bulk here really is just within the bulk of the CFT itself. So if I have a finite internal symmetry in a CFT, then it's described by a fusion category. this is some category which encodes some different objects, and in any category we also must have morphisms, and morphisms are given by these functions. So basically what you can imagine doing is thinking of these lines as representing some discrete version of a background gauge field. And if you take your spacetime manifold, you can triangulate it with different configurations of these lines. And analog of doing a gauge transformation is this F symbol move here. And this tells you the relative, in this context, it tells you the relative phase difference between two different triangulations of the manifold. And this is precisely where the code cycle that defines the anomaly enters. So I should say this is just a formalism, really, and it allows us to actually derive what are the consequences that we'd see if we studied an actual CFD.
Why do you need triangulations?
Well, you'll see in a second, but it's like if you want to study the consequences of some symmetry, you probe with some background gauge fields, and when the gauge fields, see in this context, like for instance, wrap around some non-trivial cycle of your space-time, then this will be either putting you in some twisted Hilbert space, or it will be representing that in like a discrete analytical potentials. So you can think about doing these sorts of things as probes of the symmetry properties of the system. So, is that good?
Yeah, I understand, but are you just trying to describe transition functions for the background gauge? I mean, for symmetry you're gauging by triangulation.
Well, I'm not gauging a symmetry.
I mean, putting background.
Right.
Is that what you're doing?
Maybe transition functions. I don't think that. Well, really the workhorse of this project of putting anomalies into bootstrap in 2D is looking at the twisted Hilbert space operators. So usually when we have a CFT without symmetry, we just think about its local operators. Think about periodic boundary conditions and study local operators. But if we have some symmetry, we can imagine looking at a twisted boundary condition where we impose that when we go around like the cylinder here, then we act as symmetry. That's sort of a free field description of that. So then this defines a completely new set of operators in the theory that we can look at correlation functions of and study, for instance, consequences of anomalies. So the anomalies will really be encoded in the properties of these defect operators. So if we want to act on one of these defect operators with a symmetry, we can encircle them by some line that intersects the line that they live on. So when we have a local operator here, which can be thought of as living on a trivial line, then this is the usual way we act on symmetry on local operators. We just encircle them and then shrink down the circle to a point. And a correlation function that produces, like again, like a discrete version of a word identity. So when we have an anomaly, these junctions can fuse in an anomalous way and lead to a violation of the usual fusion rule of the lines by some phase. And you can compute this in general. And for instance, when you find that, when the symmetry is Zn, you can show that this phase you get forces the spin of these defect operators to be not an integer. So this data was incorporated in a nice paper by Ben and Chow, and they showed that there's an upper bound on the lightest charge operator for Zn. K represents the Zn anomaly, basically. So
So what is S?
S is the conformal spin of the defect operator. So in more generality, we need to, so you can sort of derive this with some other arguments. You can sort of look at the cylinder mod. You can actually derive this just from this formula from cylinder modular invariance. But more generally, just using this formalism in order to describe what happens for a given anomaly, you can imagine well, having the defect operator sitting somewhere over here in the right end of this configuration, and then these lines are encircling this defect operator, and we just want to compute the phase difference that we get when we fuse these two lines together all the way. When we compute this phase factor, we'll get some two-cocycle-like function, and this function here will contain all the information that we need to encode the anomaly. So there are various invariants that you can look at, and this will tell you what kinds of anomalies you have. So in the context of this LSM anomaly, the main consequence is that if we have a defect operator, let's say of one of the generators of the Cn cubed, then the other two generators will not commute in the defect when they act on these defect operators. They'll only commute to a phase. So for odd n, this is really the only signature of the LSM anomaly. For even n, there are some like Zn anomalies that you get when you have the LSM anomaly, but that's not really the focus of the work. So, but again, it can be included in the bootstrap setup. But actually, in this case, just for time reasons, I'll just stick to the odd n cases. I'm sticking this up. So now I'll just briefly mention how the anomaly is incorporated in Bootstrap. If you want more details, I can tell you later. But the basic idea is that if we consider a short segment of this defect of a defect line, we can sort of take the OPE of the whole thing and expand it in terms of bulk local operators. The fact that the defect operators transform into projective representations of the symmetry means that the content of the OPE will contain charged local operators. And this is because if we take like a Zn times Zn projective representation and take its tensor product with the anti-projective representation, then the result is a direct sum of all the 1D reps of Zn squared.
So what is lambda?
Sorry, lambda. Lambda is an OPE coefficient. So because of this, we can really make it clear that there's a difference between a non-anomalous Cn and an anomalous Cn. If we just had a non-anomalous, with anomalous Cn with this mixed anomaly. If we just had a non-anomalous Cn, then we just have basically some complex field and its conjugate, and the OPE of a complex field and its conjugate will only contain singlet operators. So without the anomaly, there's no access to the charged operator spectrum, just by taking the OPE of these defect operators. So you can use numerical bootstrap to compute an upper bound on the dimension of the lightest charged operator appearing in this OPE. And it turns out that later you can use this as input into modular bootstrap to obtain a universal bound on the dimension of the lightest charged operator in the CFT that only depends on the central charge. So for the first calculation, you need the dimension. You need to assume some dimension for the defect operator that you have. But then eventually you can incorporate this into modular bootstrap and get something that's fully universal. Yeah.
Can I make sure I understand that picture? Is that the symmetry generator labeled by G and the two defect operators living on its endpoint? Is that what that first picture is?
That's right.
Okay, and you fuse them together, so you lose the. Okay,
Right.
I understand. Thank you.
Okay. So next, I'll talk about adding a boundary. So so far I've mostly talked about periodic boundary conditions or twisted boundary conditions, but we can also have a real boundary, and and in general, what we'll have is a set of fields now which live on what we can think of them as starting from the interval, and we can do the usual reequalization mapping, and then mapping into the real axis, where above the real axis we'll have some CFT, and below the real axis we'll have nothing, or probably more precisely, some gap theories. And we're considering basically interfaces and domain walls between these gap theories and CFT. So, so now, if we want to describe symmetries in the presence of the boundary, if you want to do everything carefully, you need to talk about the mathematical structure of the fusion category and how it interacts with the having a boundary. So in Bootstrap, what we can do is imagine that we had access to some particular boundary condition, and now what we want to do is imagine taking the symmetries in the bulk and fusing them onto the boundary. So in general, this will give us a map between different boundary conditions of the theory, but as conformal boundary conditions, they'll all have the same spectrum, but they will have a different label. So you can, in principle, if you knew what the Carty states were for whatever boundary condition you had, then you'd be able to determine what the image of all these operations are by just knowing the charges of all the local operators which create the Carty state. And so this is, in principle, a completely well-defined thing, a unique thing. And so what we're going to do is, using category theory language again, we're going to consider the orbit of all possible G lines fusing onto the boundary, and we're going to say that the full orbit will define objects in some module category. So it turns out that the anomaly will forbid this module category from having a single object. This is what also related to what Carolyn was telling us the other day. And this is the statement that if I have an anomaly, the boundary condition that I start with cannot be fully G symmetric. It must break G at least somehow. So again, we can specify similar data to what we did to specify the fusion category. And this will involve considering junctions between topological lines and different types of boundary conditions which are topological. So junctions of this form are free to be moved along the boundary as long as they don't pass any bulk operators or any boundary operators. So it's important here that the fusion rule that would be coming from this fusion process here is obeyed as we go along this, around each of the lines, external lines. If fusion rule is not obeyed, then this junction is not topological, and there could be a non-trivial primary field that is interesting. So again, there is going to be some F symbol like thing, which applies to the bulk lines heading on the boundary. There's again pentagon identities, and this is actually how you can derive that you can't have a simple object if there's an anomaly, a single simple object. And the classification of these module categories over the bulk fusion category is given by, in this context, when you have vector omega as a fusion category, by the second group homology group of the preserved subgroup of the boundary. So roughly, you can think about sometimes these different boundary conditions as representing different SPT phases that you have an interface with. So in this, in the remainder of the talk, whenever I talk about a boundary condition, I'm going to assume that I have a boundary condition which preserves two of the ZX symmetries of this ZMQ. So this is the largest that's allowed by the anomaly, but in my ultimate goal of being able to assume I have a single stable boundary condition. This is perhaps not the most natural because it's the most natural thing is to break all the symmetry if I want a stable boundary condition. Okay, nonetheless, we can try to proceed and see if we get any interesting counts. What we do is very similar to what we did to understand the symmetry properties of the twisted sector operators. So we're going to take some initial starting point boundary condition that satisfies this property, and then act on it with the broken Zn, by the generated broken Zn. And then we're going to look at the interface between, or a boundary condition changing operator that serves as an interface between the original boundary condition and its image. And the anomaly will tell us that these kinds of operators will transform into projective representation of the symmetry group. So actually there's kind of a nice analogy to SPT physics because in many cases, or in some cases, these Zn symmetries can arise when you have a phase diagram where you have different SPT phases. And those SPT phases will carry the first Zn squared symmetry group. And then the third Zn is sort of an SPT entangler, which builds the SPT phase. And that becomes a symmetry at some multi-critical point. And so if you take this third Zn, the broken Zn, to be the one which maps between different SPTs, then these different boundary conditions like literally represent different SPT phases. And so it's natural to have this projective representation in this mixed boundary condition set, because you have a relative SPT hanging around between both sides. So there's more math that's pretty nice and beautiful that you can do to sort of understand the symmetry algebra of these lines encircling the boundary operators and other representations. And there you construct some kind of bimodule category. I can sort of tell you about that again if you're interested, but it's pretty technical probably right now. And this mathematical structure is really the same as the structure you need to describe gap boundaries of 2 plus 1 topological forward. So one more assumption that I'm going to make is, when I talk about boundaries, is the full arbitrary stability of the boundary condition. So I'm going to assume no boundary relevant operators on this boundary condition, whether they preserve symmetry or break symmetry. So again, this is kind of not a super physical assumption, but it does hold in many examples of CFTs that I know. That at least all of them seem to possess one boundary condition that's like this.
So we're running a little over. Can we wrap up in 5 minutes?
Yeah. Oh, sorry. Yeah. Okay. So now I'll just explain the bounds. So maybe I'll skip these ones. Well, let's see. I'll skip that one. Let me skip this one, and then I'll just go to this one. So the first ingredient of this calculation was to consider correlated bootstrap calculation of well, in this case, boundary condition changing operators, and compute the lower bound or upper bound on the. Oh, sorry, I'm getting a bit confused. So if you demand that I have this particular kind of stable boundary condition, you can ask, is there a lower bound on the dimension of the boundary condition changing operator, which is consistent with this assumption? And you can derive an allowed region for the dimension of the lattice such boundary condition changing operator. So if you look at SU501WC other model with, say, like Dirichlet boundary conditions, you find that it sits somewhere here, nearly saturated bound. But then there's some other feature where the slope of the line sort of changes. So this is just important to know for there. This kink here appears somewhere between 2.75 or something, 2.85. Oops. So now I can. So now I'll show the main results. So with all the tricks that I mentioned, you can derive a universal upper bound on the dimension of the lattice charge operator of a CFT with central charge equals whatever it is on the x-axis, and this type 3 post-cycle anomaly, or LZ anomaly. And as I mentioned, for different n, the minimal theories that we seem to know of are n-1 free bosons. For n equals 3, that's C equals 2, and the WZW model that sits in this conformal manifold is SU3 level 1, and it sits at this very prominent kink of this bound. So I should emphasize that if you just do standard modular bootstrap for this calculation, then there is no bound at all on the spectrum of charged operators. But this type 3, when you incorporate this correlated bootstrap trick, then you do get bound. So we can do the same thing for, say, n equals 5. This time, we have one of the WZW models, which sets the central charge 4, slightly less close from saturating and bound. And there's some other kink that in this plot sits essentially at central charge 2.8, and the scaling dimension of this charge operator is 4/5. So if you look at the dictionary or encyclopedia of WZW models, you'd find G2 level 1 WZW model to be sitting right at this kink. Okay, so I tried to push the numerics extremely hard, and eventually I ruled out G2 level 1. So I now have two essentially completely independent calculations of some bounds with this anomaly, and both of them seem to have a kink, which sits at roughly the same central charge. So yeah, this is, I think, very interesting to study further, and I'm trying to do that. And okay, again, we have some bounds, so we can sort of calculate a very similar bound using cylinder modular invariance, and we can get a bound on the symmetry defect operator, but again with this sort of undesirable assumption of a completely symmetric, or a maximally symmetric, completely stable boundary. Okay, so we get bounds for both n equals 3 and n equals 5. Okay, so there's many things to do, but yeah, since I'm out of time, I will just end there. Thank you.
What does the correlator bootstrap mean? You mean it is not modular bootstrap or anything else?
Right. So it's I look at 4-point functions, and I impose crossing symmetry on them, and then
So you expand the 4-point function in terms of the Mirasaura conformal or the global symmetry conformal.
Yeah. So originally we just did global conformal blocks, but in some of these boundary calculations, I incorporate some more Virasoro symmetry by computing OP coefficients of descendants.
Sometimes it is conformal, global conformal symmetry. Sometimes it is Virasoro.
Yeah.
Okay. And I notice in your plot there is a lot of wiggles. But does this means that
Which one?
Yeah, please go. Yeah, for example, this one.
Like
usually they should be smooth if you are not at the kink. So do you think this is due to you didn't put enough point into the plot, or there is some numerical issue?
No. I think it's neither. I mean, so these are in this. I mean, with the technology that I have, these are quite close to saturation, and there's many points.
Yeah, for example, the charged upper bound. How many points is in this plot?
Near the kink, I think it's many, but yeah, I mean, this is definitely not like a feature of not enough discretization.
Okay. What does local means here?
Yeah, sorry, I mean, yeah, they didn't explain, I didn't have time. So, you can calculate a bound on, if you assume a gap in just the charge operator spectrum, or you can assume a gap in all operators, irrespective of what symmetry representation they carry. So that's what I mean by local.
So sorry, local by local you mean no symmetry.
Yeah.
But no symmetry you get stronger bound.
Right. So in this, to get the bound on charged operators, I only assume a gap in the spectrum of C and Q charged operators.
Yeah.
When I get the local operator bound, I also impose a gap on the spectrum of singlet operators. So that's the singlets together with the charged operators. That's all local operators.
Okay. Okay.
Yeah.
Maybe time for one more question. This one?
Yeah. So you've been talking about LSM anomalies, but it seems like the story is more general and should include any
Is there, like, for the upper bound on the charged operator?
Sure.
Yeah, I think if whenever you have an anomaly, I think actually now that we've done type 1 and type 3, I think that pretty much covers all anomalies of discrete symmetries, or of discrete abelian symmetries.
Yeah, so these
Type 2 is kind of dependent on what type 1 most of the time, so yeah.
So the discrete symmetries don't have to start their lives as lattice symmetries, right? They could just be internal symmetries of a lattice.
Yeah.
Okay.
And they could be anomalies too, yeah. So you could have just something that lives in the boundary of an FPT that has a CN cube symmetry, and that would be just as good for the CFT point of view.
There is lattice theories that have the LSM anomaly as an internal symmetry, no?
I think you just, you know,
It's a terminology thing.
yeah, it's
when I hear LSM, I'm always
yeah.
thinking mixed anomaly between internal and lattice symmetry. But maybe,
Yeah, I think there's really no LSM anomaly in CFT. It's just
It's not distinguished
Yeah.
from any other.
of course, yeah. It's just this particular, I mean, saying type 3 code cycle is like a bit weird, I think, so. It's a particular, this form of the anomaly is natural to emerge from some LSM.
So with that, let's thank Ryan again.